Okay. All right. So, hello, everyone. Good morning and good afternoon or good evening, wherever you are. So this is the next, I'm Ibrahim Bagheri. I'm a professor of electrical, computer, and biomedical engineering at Toronto Met here in Canada. And this is another event from the SIGIR Virtual Forum, jointly organized with my colleagues in the SIGIR Virtual Forum committee, including Suzanne, who's here, and she might be able to wave at you. These series are what we call the Lean and Learn series, and the idea is for these talks not to be similar to paper presentations, but rather to give you an idea of an interesting and important up-and-coming topic with a hands-on component. The idea is the hands-on is not for you to do the hands-on, but for the speaker to show you hands-on aspects of their work and then point you to code bases and their GitHub repository and all that you can try out later. What Shibo will do today is also send us after the talk some code that you can try out and test and see how it works. So without further ado, I'll pass it on to Shibo, who will introduce himself and then get started.
Cool. Yeah, thanks for the introduction. My name is Shibo Hao, and I'm a second-year PhD student at UC San Diego, working with Professor Zhiting Hu. My research interest is around learning model and especially in the reasoning ability of LLM and something about the agent based on foundation model that can perceive, learn, and interact with the environment. So yeah, it's an honor to be invited here to give a talk about LLM Reasoners. So yeah, before I get started, I want to share that yeah, I want to share the link of the code base. Okay, so yeah, basically this is the GitHub repo, and today besides the talk, I'm also going to show a demo. You can see the file name is demo.ipynb. So yeah, if you want to try, you may also run this notebook by yourself. Okay, I think I can start the slides. Cool. Can you guys see the screen?
Yes.
Yeah.
Great. So yeah, this library is a collaborative effort by many members of our group Mix Lab at UCSD for the past few months. And yeah, let's get started. So nowadays, I think it's a consensus that reasoning becomes a pivotal ability of LLMs. So for the past year, every time a new LLM is released, the author would claim that this new model has better reasoning ability than the previous ones. And we have also seen many interesting applications of LLMs, such as playing the game of Minecraft or surfing on the internet as a web agent. So all of these are based on the reasoning abilities, improved reasoning abilities of modern LLMs, so that they can solve these complex and typical long-range problems. So in this talk, I'm gonna give an introduction of some important aspects of LLM reasoning, including some recent works on the reasoning algorithms, the evaluation, and the analysis. There's also going to be a couple of hands-on coding sessions where we'll play with LLM Reasoners with a Jupyter notebook. We hope this talk can help the audience to have an overview of the current state of LLM reasoning and understand the design of LLM Reasoners, our library, and also know how to apply it in their research or development. Okay, let's jump into the first part, the algorithms. So yeah, basically when we talk about reasoning, LLM reasoning, we refer to solving a complex problem that is not straightforward, but often takes many steps to solve. And the math word problem is a very typical example. So if we want an LLM to solve a math problem, here's the most basic prompt we'll use. So we will first show some examples of question answer pairs in the context, uh, and then ask a new question for the LM to solve. So ideally, the LM should follow this format and complete this answer for the new question. And there was a very popular paper 2 years ago that proposed to prompt language models with examples uh, of step-by-step reasoning. So for example, instead of just showing the answer here, we may also want to show the reasoning process. And the language model should be able to follow this format and also produce a chain of thought before reaching the answer. So yeah, this method is shown to be very helpful. And by the way, you may have noticed that now if you directly ask a question to ChatGPT without any demonstration like that, it will by default answer the question step by step like that. And that is because people nowadays are fully aware of the power of this manner of step-by-step reasoning, and they even collect this type of data to fine-tune the learning model. And yeah, this step-by-step reasoning ability is also considered as one of the emergent abilities of LLMs. So the emergence means qualitative changes in a system result in a qualitative changes in behavior. So COT reasoning chain of thought uh, is increasingly helpful when the scale of LLM become larger, which is very interesting. So and now currently generating a step-by-step reasoning chain is almost a standard method to reason with LLMs. For example, in all of these benchmarks or the blogs of new model release, people will by default use chain of thought as their reasoning method. So yeah, basically that's because step-by-step reasoning is really helpful. But here we want to propose a question: is chain of thought the best way to generate a reasoning chain, or are there better method to derive a reasoning chain with maybe higher quality from large language model? So yeah, first I want to give a brief introduction of one of our papers last year, which also forms the basis of our LLM Reasoners library. So this work is called Reasoning with Language Model is Planning with Word Model. Yeah, by the way, if you have any questions, feel free to interrupt me. So yeah, here let's look at an example. So this is a task where you have a set of blocks of different colors, and you want to take a sequence of actions to move those blocks from the initial state to the goal state. Maybe if you want to use the most famous method, chain of thoughts. This is an example generated by chain of thoughts, which sounds reasonable at the first glance. However, if you look into the details, you will find the third step is actually a invalid one because the yellow block is still under the right block at that step. So actually, this action is not legal in this environment. This is because chain of thought cannot truly track the reasoning state due to the nature of autoregressive decoding. So basically, yeah, at each step, the only condition for the language model is all the previous step. So the language model needs to implicitly track the current word state, which is very challenging for a language model. And then maybe we can think of how human can avoid this. So human process internal word model, which can simulate actions and effects in the word, uh, according to some conclusion by psychology or neuroscience research. So in this example, what does a word model do? Basically, we can imagine a word model to track the word state after each action. So for example, if we pick up the orange block, we may have an image in our mind like this, and then taking another move, we also keep track of the new state. And if the reasoning comes to a bad end, or if they realized there's a mistake, human can also try to explore alternative reasoning paths. Like here, we may also attempt different moves in our mind. And at the end, human can have a rough assessment of the outcome by estimating possible future scenarios. And in this case, the state in the green box already have the orange block on the red block, which partly aligns with the goal state. So we think this might be a better state. And then actually we can do a analogy here. Chain of thought is more like the system one reasoning in our mind. Basically, we use our intuition, but with this kind of system two reasoning, we can really do some deliberate thinking and solve really complex problems. So yeah, then the problem becomes how we can enable large language model to reason in a human-like manner. And here we propose reasoning via planning, a novel framework for language model reasoning that corresponds to the three advantages of human reasoning. So first, we repurpose the language model as a word model to explicitly model the state. So yeah, here we show the image just for the ease of understanding, but in our implementation, all the state is described by the language so that it can be processed by the language model. And then we try to incorporate a principled planning algorithm, namely Monte Carlo tree search, which is also used by AlphaGo, widely used in board game. And yeah, we also want to introduce some rewards during the reasoning so that the planning can be guided by some signal. Okay, so yeah, here we can show a concrete example. So in Monte Carlo tree search, we iteratively build the reasoning tree with some steps. The first one is selection. So basically, this is the current reasoning tree, and in the first step, we need to find a terminal node, not terminal node, a leaf node. So yeah, basically we need to make a couple of decisions, and these decisions are based on the Q value in Monte Carlo tree search, which is composed of the estimation of accumulated reward, and also it considers how many times this node is visited so that we can encourage the node that is visited fewer times.
Can I ask you a question here?
Sure.
So like with each of these reasoning trees, you have a reward associated.
Yeah.
How is this? I mean, I don't know. Like, can you maybe say a few words on like how this reward is typically computed? Because
Yeah.
it seems like you
Yeah.
could be very infinitely far or very close, and you might not necessarily know how close you are to your goal. Like, how is this measured?
Mm-hmm. Yeah, good question. So yeah, I'm gonna introduce the reward maybe in the next slide.
Oh, sorry, then I'm patient.
Yeah. So yeah, the second step is about expansion. So now we are arriving at this leaf node. We want to explore what the next action can be. Uh, so here basically we have two candidate actions, and for each one we'll have a next state corresponding to it. And uh, yeah, after we pick one, we can simulate the reasoning chain to the end. We call it terminal node, so that we can have a complete trajectory. Then we can use the accumulative reward to backpropagate to all the previous node to update the Q value. So basically, we want to balance the exploration and the exploitation. So yeah, the first one is represented as the times of being visited of each node. So yeah, we want to explore that the nodes that are less visited, and the second term exploitation means we want to we favor those nodes that has better estimated accumulative reward. And we want to emphasize that in this framework, the reward design can be quite flexible. So in this particular domain, we have maybe two rewards. The first one is called the likelihood of actions. So basically, at each stage, we will prompt the language model with the current the description of the current state, and we'll try to append the new action to the end of the stage and see what's the likelihood of the language model predicting this new action. So basically, this is also like how the action is predicted in chain of thought prompting. And basically, this reward measures the intuition of learning model. And then we can also have another reward, which is task specific. Like in this one, we 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 have the goal state, and we can match the current state with the goal state and see how many sub goals are satisfied. Like maybe here in this state, the orange one is on the blue one, so this partly aligns with the goal state, so we can assign it some partial rewards. And there can be also other options like I believe this one is very useful and general. So this is self-evaluation by the large language model. Basically, given the current state and a potential action, we directly prompt the language model to evaluate the action, like whether it's good or not, whether it's useful, whether it's correct. And but this way, this may sound similar to this likelihood of actions, which is also generated by large language model. But we want to highlight this this is actually a different mindset to evaluate an action where you have the action in the context, and you want to do a post hoc evaluation of that. So basically, sometimes the problem can be hard to solve at the first glance, but maybe it's easier to discriminate the error in the action when when you have already uh, thought about this action. So yeah, this self-evaluation reward is very general. And we can also have other rewards like confidence of the next stage. So sometimes the reward model is not always um, deterministic, and we want to favor those trajectories that is more confidently predicted by the word model.
So if I kind of come back to like answer my own question, so you're saying I have like multiple choices. I mean, either I'm in a problem where I can fully explore all states and see which states will lead me to the goal and how many actions am I away from it. That was like the blue reward, is that right?
Mhm. Yeah, I wouldn't say we want to fully explore the reasoning space because it's almost
Can get
impossible
expensive, yeah.
to enumerate. Yeah, but
Um,
basically, yeah, it's like what you said.
Right, and I think the other choice is to just count how many sort of like sub solutions are already like in place, like the orange is on the blue, so that gives me partial credits.
Mhm.
But I can see that might work in some problems, but like in other problems, you might think that you have like 99% of the sub problems in place, and then the last action you just cannot take to complete the puzzle.
Yeah.
So it could be kind of, I guess it kind of depends on the problem domain you're trying to solve, whether that's a good or a bad approach. And I guess the self-evaluation is sort of like close to like the chain of thought, just saying, well, by the way, how close do you think you are from that step? Can you self-evaluate this one step? And that may work if the LLM is kind of like, again, close to solving it, and it can be just completely uninformative if the LLM is just confused, I guess.
Yeah, exactly. Yeah.
Okay. Interesting. Thank you.
Yeah, and this reward can be combined instead of they are separate options. Basically, in this task, we can add these two rewards so that we can try to make use of different reward signals. And yes, so basically RAP can be applied to different diverse reasoning tasks in different domains. And the blocks word task we discussed so far is a plan generation task or embodied plan generation task where we can intuitively define the state as the current block configuration and action as a possible move. So yeah, in this domain, we show that RAP with Llama 33 billion can even beat very powerful GPT-4 with chain of thought. And there are other domains like mathematical reasoning. So basically, we'll have a question with some background knowledge, and there is a question. In this problem, we define the state as the collection of all the known variable currently. So essentially solving the mathematical problem becomes a process of expanding this set of known variable until the question can be answered. So yeah, each action here is to ask a sub question for an unknown variable. So yeah, by this definition, we can use the same framework to solve math problems. And also RAP can outperform very strong baselines. And there's also another domain we have experimented on like logical reasoning. So yeah, this is a synthetic data set. So you don't know these words. And here you have some rules and you have a fact as the initial condition, and then we want to verify a hypothesis like this one, whether phi is unicellular. I don't know how to pronounce it. And yeah, basically the state here is we define the state here is to be the fact we are focusing on. So the initial state is just the initial condition we have. And each action is to select one of these rules. So the state transition is simply using the current state and the selected rules to derive a new fact until the hypothesis can be verified. And also we show that RAP outperforms COT with some augmentation called self-consistency. This doesn't matter. And in both final answer accuracy and the accuracy of the whole proof. Okay, so yeah, back to our main thread. Actually, besides our paper, there are also many papers in the past year that aimed to generate better reasoning chains with language models. Yeah, I can show more papers, but basically, I want to say, despite people's attention and the growing body of literature in this field, there are actually some important problems addressed. For example, what is the technical connections of these algorithms, because they are all developed in isolation. And we also don't know which designs in this framework, in these algorithms really matter, because yeah, there are so many factors that affect the performance. So another concern is that now we can have some more complicated algorithm to get a better performance, but the difficulties in developing this algorithm is also getting higher. So imagine when we interact with ChatGPT, maybe all we need to do is to think of a prompt, but now we have so many things to do with this complex reasoning algorithms. For example, we need to develop the search algorithm. We need to define the reward, and we also it's also a torture to debug because they're so hard to analyze. So I guess that's the two main motivations we want to develop LLM Reasoners, this library. So in this library, we first want to build a unified formulation of different reasoning algorithms. So yeah, here I list three very representative algorithms: chain of thought and already wrap I just introduced, and another algorithm called tree of thought, which is also a very popular paper last year. I will introduce more in the later slides. So basically, we can write down the same objectives for all of these reason algorithms. There are three parts we should focus on. Sorry. So basically, this objective says we should optimize the sum of rewards of different all the reasoning steps. And yeah, this RSTAT is the reward function, which tells you whether a reasoning step is good or not. And this state transition probability function is what we call the word model. And we also need a search algorithm to optimize for the objective, because the reasoning space is really expensive. So yeah, we'll show how all of this algorithm can be fitted into this single framework. For example, in chain of thought, using the same example here, yeah, the action is similar to what we've just seen. It's just the move we'll take. But the state, since chain of thought doesn't explicitly model the state, we can define the state here as a collection or the list of all the previous actions. So yeah, for example, I2 here is like that. Basically, it's just the concatenation of A0 and A1. And the reward function is just like the likelihood produced by language model, because basically at each step, COT will generate. Imagine if we want to use greedy decoding, COT is just predict the most likely action given the current state, which is the previous actions. And apparently there is no exploration of different reasoning paths, so it's simply a greedy decoding of the reasoning steps. And tree of thoughts paper published last year by Princeton extended chain of thoughts to tree of thoughts. And yeah, basically here they have some different reward function like self-evaluation. So basically the language model is conditioned on the current state and maybe a potential action, and trying to evaluate whether this action is good or not. And they also apply some search algorithms like BFS or DFS to search for the best reasoning chain. Oh, yeah, and as you can see, the state remains as the collection of all the previous actions. And here the word model is a deterministic one, and it simply append the new action to the current state. So yeah, so the new state will have a length of one more actions. And yeah, here comes wrap. And I think the main difference is that now we want to explicitly model the word state. So here we'll use large language model as a word model. So yeah, basically this state here is a description of the current state instead of just a simple collection of all the previous actions. And based on this unified information, we built LLM Reasoner, a library for complex reasoning with LLMs. So each of these three components correspond to the three classes in our library. So yeah, we have this search configuration class where we'll define the action space and the reward function, and the word model class, which takes over basically everything about the state. We want to define the initial stage. We want to define the state transition, which is this probability, and we define what state is considered as a terminal state. And yeah, we also have different search algorithms implemented. So yeah, we also incorporate multiple LLM APIs, and users can decide whatever they want to use. And yeah, just like what we've just showed, many of these functions can be powered by large language model. So ideally, we can simply use LLM API from here and define these functions. And there are also many other helper classes like benchmarks, and also the visualization tool, which I'll show later. So as a concrete example, if we want to solve maybe these problems, the code will be like this. So the user needs to define the word model class and the search configuration class by inheriting our base class. So yeah, I list the most important functions here. So basically, here we have a member variable LM, which is initialized from maybe one of these LLM APIs, and then we use some prompt to make it function as we want. And at the end, we can have a object called reasoner, which is just composed of these three important components as our formulation. So basically, the search algorithm is already implemented in our library, so you can hopefully they can be used off the shelf, but you can also definitely develop your own search algorithm using the same API provided in our library. Yeah, I hope that will be easy to implement. And there's also gonna be a visualization tool, which is very helpful for users to debug. This is interactive. You can see the reason tree at different time step and different state. You can also define what information to be shown here. Don't worry, I will show the visualizer later. Okay, so so far, do you have any questions? If not, maybe we can go through this notebook and see what LLM Reasoners looks like.
By the way, I tried running it from Colab, and it said it can't find the packager Reasoners. So how do I get that
Yeah,
code?
so yeah, basically it's gonna take some time to configure the environment. You may follow the instruction in our README. I believe there's some instruction, for example, how to create the environment, how to install all the dependencies.
Oh, I
Yeah,
see.
and
Mm.
maybe you also need to download the model first, and have enough memory. So yeah, maybe
How much memory does one need?
yeah, that depends on what model you want to use, right? So
If I just wanted to run your demo, how much memory, how much, like how deep do I have, how much money do I have to pay to run your demo?
I guess if
Like, would
you
an A40 work, or do I need an A100, or can I go cheaper?
I think if you want to use a Llama 2 70 billion model, here we have some quantized version of LLM. So basically, this model takes like a 30 GB memory. So
Okay.
you can use either one 800 or maybe two 3090, you know, less expensive card. But definitely you can use, you know, smaller LLMs like some 7B models. I believe nowadays those 7B models can be also very powerful. But yeah, we haven't tried that in this domain. We want to make sure this example works. So I just use
Hmm. Okay, so I won't be able to run it. Like, I mean, I don't, yeah.
yeah.
Do you guys plan on like releasing some demo code that could be run on like non-one A100 GPUs? Like, well, like, I mean, like, I don't maybe need to run it with like Llama 2, but like if I could run it with like a smaller, maybe like a smaller Flanty 5 or something, what would I need to? It would be great to know which lines I would need to change to like just kind of like,
Okay, yeah, I'll introduce the
and maybe not now, but like, yeah, I would be curious.
so yeah, I guess the Flanty 5 is not very strong, but nowadays we have maybe Mistral or many.
Yeah, no, I understand your worry that I will try it with a weaker model and then the performance is bad and then that would give you a bad name. I was just trying to like just get the code working in a teeny tiny example, just like see that I have all the pieces
Sure.
before making things expensive, you know.
Yeah, sure. So yeah, we can look at this example. So here we make use of a model called XLlama, which is a library for quantized llama model. And here actually in the comments, we also list other options, not all the options, but for example, we can simply use Hugging Face transformers, and basically here you can use whatever models you want, just like what you said.
Right, it's just like a one-line change in there. I see. Thanks.
Yeah. And we can import the benchmark module here. So basically, I tend to standardize the this task with standard prompts and share the codes among them. So yeah, basically we can initialize the evaluator here, load the data, and yeah, also the prompt is sampled among from a pool of prompts. So we know previous work, many works can cherry pick the prompt that works best for their own method, but now we want to make a fair evaluation, so the prompt is actually randomly sampled, right? So oh, okay, this is not I need to open this. Okay. And using this example, let's construct the input for chain of thought. Okay, we will start with chain of thought. So basically the initials here we also make use of the example of blocks word, the one we've seen so far. So the initial stage is quite simple. Here there are only 3 blocks. All you need to know is the orange block is on the red block, and the red block is on the table. So and there's another blue box on the table. So it's only 3 blocks. And our goal is to have the red block on the blue box. So basically, to move the red block, you need to first remove the orange block, which is on top of the red box, and then move the red blocks on top of the blue blocks. So you can solve this in 4 steps. Yeah, we can see how chain of thought works. So basically, this is a prompt. And at the first, we have some introduction of this domain, and then yeah, and then there are 4 examples, which is randomly sampled. This is statements, including the initial state and the goal and a plan. And then the second example, third example, and finally, this is the question we want the language model to solve. And using this prompt, I guess the language model, what the language model generates is something like that. So it says we should pick up the red block and stack it on top of the blue blocks, which is not correct, right? Because we know that the red block is now under something. It's under the orange block, so we cannot really move the red block as the first action. Right. So yeah. So in this case, COT simply failed. And we can also check how tree of thought works in this case. So yeah, we may want to define a state. This is just to standardize the code. Is not even necessary. So if you want to build a quick demo, you can ignore this part, also this part, and yeah, we want as we just introduced, the user may need to define 2 classes. The first one is word model, which defines everything about the state. So here we will define the initial state, basically the action history is empty and the step index is 0. So at each step, basically you just append the new action to the current state. Is a trivial function here because we don't have an explicit word model for tree of thought. So basically, except the situation that the action comes to an end, what we want to do is simply what we want to do is simply to append the new action to the current state. And yeah, we also want to define the terminal state. Yeah, and the configuration here. So first we need to define the action space, and this is also generated by a large language model. And I guess I think the prompt is similar to the prompt for COT. So for example, if you put this prompt to the large language model, and I think language model will naturally output the next action here. And yeah, if we have, oh, sorry, this is read only. So if we imagine there is already a action 1, action 0 here, and for the next line, the language model will naturally predict the action 1, the next action. Right? So basically, that's how we sample all the possible next action from the language model. We will do some random decoding using this argument. We can also set the temperature to make the generation more diverse or more controlled. And this is a post-processing of the output, and deduplicate the actions and finally return. And there are 2 reward functions which can be tricky, but basically we have a fast reward besides the reward because we want to sometimes speed up the algorithms. So sometimes the reward can be calculated without the real state transition. So basically we can calculate the reward simply with the current state and the action. But for maybe other reward that is more expensive to calculate it, we will need the word model to take us to the next state so that we can calculate the reward. So in that case, the calculation may take longer. So we want to separate these 2 rewards so that this fast reward can be calculated easier. And for some algorithms such as Monte Carlo tree search, we can make use of this fast reward as some prior for the search, and we can have the full reward, for the full search. But yeah, basically, it's fine if this can be a little bit complicated to understand. We just think of this as a single reward function. Yeah, let's see what is defined here. So I think this would be likelihood. So yes, we mentioned there are 2 types of reward used in the block word domain. We have the likelihood of the action produced by the large language model given a prompt. So the input is also similar to this prompt. And what we do is to use this prompt as a condition. And also we want to measure what will the likelihood be if we put a new action here. So yeah, basically this is calculated in this sentence. We have the input, and we also append the new action with a new line to the input and see what's the likelihood of this action. predicted by the language model. And there's also another reward called self-evaluation. And basically this this prompt tries to give you the current state and the goal, and also the current action, and ask the language model whether it's a good action. So yeah, the initial stage, yeah, never mind. Yeah, so basically, for this algorithm, we will simply add these two rewards to get a full reward. And for this full reward function, since we have everything done here in the fast reward, we can simply get everything from this KW args, which is automatically passed to this reward function from the dictionary. Yeah. And we have this word model object, config object, and we simply initialize the algorithm, and we can make a reasoner. So yeah, this algorithm may take a few minutes, so I'm gonna skip the process of running it and only show the results here. So basically, it has still output the same action sequence as the chain of thought, which is not a valid plan.
Sorry, Shibo, can I ask you maybe a stupid question? When the language model keeps the state of the world and you have an action, how do you check that applying that action to the state of the world actually transitions the language model to a correct target state of the world? So for instance, you have the red block under the blue block, and you give it an action that is take the blue block and put it on the side. How do you know that that actually affects the language model correctly and the language model now has the correct representation of the world? How can you check for that?
Yeah, that's a good question. So yeah, first of all, I want to claim what I've introduced so far is tree of thought is not rep. So we don't have a explicit word model here. So basically the word model only collects all the previous actions. And what you just mentioned is about is something I'm going to introduce. So I don't think we have included a mechanism to verify whether the new state is reliable. Is basically something empirical. So we just design some prompt to get the language model as the word model to predict the next stage, and see whether this works in this domain. So if not, we'll use some other tricks to make the prediction more reliable, or if it's good enough, then it's great.
So you just assume that the description of the state of the world that you give the language model and the actions are always, it's an assumption that the language model is able to track your instruction.
Yeah, I think that's the assumption for this domain. So,
Mhm.
so yeah, maybe in other domain like the mathematical reasoning, the word model is actually to answer some sub questions, which is of course always which contains many errors, and at that time we need some mechanism to control the word model here. So basically we make use of the confidence of the word model producing some answers. So it's if this transition, if the language model is very confident about this state transition, we'll have higher reward. So if it's very uncertain about the transition, then maybe we don't favor this trajectory, and maybe that's a partial solution for this problem you just mentioned.
Mhm.
Yeah.
Thank you.
Okay, so yeah, in this now we're going to wrap. So yeah, here we keep track of the real world state, and as the initial state, we have we want to extract the initial state from the data point, and at each step, what we want to do is to predict the next state. And here, yeah, just as what Ibrahim said, sometimes it can be unreliable, and that's why we did use some trick here. So basically, depending on the action, we use different prompt for the language model to predict the next state. So yeah, because we found it can be difficult for the language model to predict the next state using a unified prompt. So yeah, by this way, the language model may see more similar examples in the context, so the task can be easier for them. And also, yeah, here we can return the state, and also cache some helpful variables here, like how many sub-goals are reached. We can simply check in this step, right? And this is also gonna be sent to the reward function in the argument, basically this part, and we will use this as a reward, part of the reward. And yeah, basically that's pretty much about the word model. And we want to look at the search config here. The get actions are similar. We also sample the potential actions from language models. And here the reward, yeah, it's also similar to what tree of thought done. We have the likelihood here. Here the variable name is intuition. Basically, yeah, it's just the likelihood, and also the self-evaluation. But different from tree of thought, here you can see we filled in the prompt, filled in the template with the current state instead of an initial state and all the previous actions, which is advantage of wrap. So yeah, since we have explicitly tracked the current state, we can plug them in the prompt to make the question easier. So imagine now we only need to based on the current state and try to evaluate the next action. But for tree of thought or chain of thoughts, you may have a lot of previous actions here, and to evaluate a new action, you need to simulate the whole process in your mind or implicitly in the attention in a learning model, which is much more challenging. And also, I'll skip the third process here, but for this algorithm, it successfully predicts the first two steps. So first, we will need to remove the orange block from the red block so that we can operate this red block. And then we successfully solve these problems. And yeah, I guess I can go to the visualization here. So basically, it's quite simple to use. We can simply use the visualize function to get a link from our demo. And these two functions is to customize what you want to see on our website. So if you don't have these two functions, you display some default information like the reward or the action, but maybe not exactly what you want to see. But by writing these functions yourself, you can control what you see on the website. Okay. So yeah, at the first step, you can see the language model explore this trajectory. It's interesting that this algorithm also made the same mistake as tree of thought or chain of thought, because in this trajectory, it select the node 1 at the first step. So that's because the intuition or likelihood reward is really, really high in this case. And of course, the search algorithm will prefer to explore this node first. But yeah, at the second iteration, the language model want to explore another reward, another reasoning path. At the end, it find all the goals are satisfied at the end of the trajectory. So if you remember, we have the reward for sub goals to be matched. So at this step, you will receive a really high reward. So even if the first step is not favored by the language model, so eventually this trajectory is selected. Basically, that's how RAP work in this example. And yeah, basically you can visualize every search tree you implemented with reasoners, whatever algorithm you want to use, whatever domain you want to work on, you can always use this function here. And yeah, our evaluator class is also able to provide you a standard evaluation results with some certain algorithms on a certain domain. So basically, this class ensures a fair comparison among different algorithms. Okay, I think that's all for the code session. Yeah. So yeah, I'm gonna continue my talk in the following two sections. So that includes some of our latest work on LLM reasoning. So yeah, besides the two limitations of LLM reasoning I just mentioned, we also identified another very important problems of LLM reasoning, which is how can we evaluate step-by-step reasoning. So yeah, we can look at this example. The question is, did Aristotle use a laptop? The answer is clearly no, because he's an ancient philosopher and the laptop is some other thing. So this is a reasoning chain generated by a language model, and if we directly look at the answer, we find the answer is correct. Is no, and that's what most of the previous work in LLM reasoning do. They simply match the answer to the ground truth and see to decide whether the reasoning is correct. But if we take a closer look, there are some errors in this reasoning chain. For example, okay, yeah. For example, the laptop was not actually invented in 21st century, and this step also contains some logical flaws. So yeah, the reasoning chain is actually problematic. And our analysis reveal that up to 39% of the corrected answers were derived from incorrect reasoning chains. that is based on a random subset of static QA with llama 2 70 billion. And there are some previous methods targeted at reasoning chain evaluation. For example, we can compare the model-generated reasoning chain to a human written reference, or we can train a model to evaluate those reasoning chain, or we can simply prompt a very strong learning model like GPT-4 to evaluate the reasoning chain. But all of these three methods may need some additional human effort. For example, for the first one, you need to really write down the reference for every case. And this one takes some training data, and this one needs extensive prompt engineering. And yeah, there are some previous work that really puts many efforts in the prompting. And another concern is that even for the strongest method that makes use GPT-4, people still claim LLMs cannot find reasoning errors sometimes. So I think that these two limitations, namely the need for the additional human effort and the overall unsatisfactory evaluation accuracy, limit this metric to serve as principal evaluation metric for reasoning. So in our paper, we proposed a new evaluation metric called RICE reasoning chain evaluation. And we first start with, simply prompt the language model to evaluate a reasoning chain. So basically, for this example, can one ignite helium? The reasoning chain said, okay, helium is odorless and tasteless gas, and helium has no color, so the answer is no. So if we directly ask the GPT-4 to evaluate this reasoning chain, it will say the given answer is partially correct and somehow acceptable, but we know it's not a logical reasoning chain. Basically, the answer cannot be derived from these two reasoning steps. So we also want to see if we make the criteria very clear to language model, like in the prompt, we say the reasoning chain must be logical, must be accurate, must be, every step must be relevant to the question, and then ask the language model to evaluate this reasoning chain. What will happen? We'll see the language model can clearly follow our instruction and conclude, okay, the reasoning chain is actually incorrect. So that's basically how we want to improve the accuracy of this evaluation metric. But there's another problem remain, that is, how can we automate this process so that we don't need any additional human efforts? So basically, we don't want to write down this instruction by ourselves, because that's going to be a huge engineering. Maybe for each different task, you need to design the prompt manually, and that's gonna take much time. So yeah, we designed a automatic flow or workflow to construct the criterion list automatically. So basically, the overall idea is to learn the criteria from some concrete errors made by language model. For example, we first want to collect some wrong reasoning chains, and the assumption is that if the final answer is incorrect, then the reasoning chain must contain some errors. So yeah, we first want to run some algorithm like COT on the training set and compare the final answer to the ground truth and collect all the not all, but some of the reasoning chains with incorrect answer. And then we'll take a closer look at them. We put the model generated solution along with the reference, because it's a training set and most data set contains this human annotated reference. Then we ask the language model to summarize what mistakes are in this reasoning chain. And then if we have collected many of these types of errors, we can ask the language model to summarize the criteria list. So yeah, that's how we get this evaluation criteria automatically. Yeah, basically the collected criteria will be used in the prompt of GPT-4 to evaluate any new reasoning chains. So we did some experiments, and so the setting is we use some human labels of reasoning chains, binary labels, whether it's correct or not, and compare the decision given by different evaluation metrics to compare against the human labels. And we observed that. So first we want to highlight REST doesn't take any additional human efforts, and we observe a better average accuracy across different tasks, and it remains robust across different tasks. And sometimes it even outperforms the answer-based evaluation, which is the most, what most papers use. Like they check the final answer whether they're correct. Yeah. I'll skip the case study, and we did some case study, and we identify 3 major types of false positive that can be recognized by RISE. The first one is very interesting. So we don't need to look at this example. So basically, there's a hallucination in an early reasoning step, but the following reasoning step simply ignore the mistake and reach to the correct answer. And the second type is that the reasoning chain is just so wrong, maybe has obvious or multiple mistakes, but it can just hit the correct answer by chance. This is especially significant when the answer space is small. For example, in this question, it's just a banner question. The language model needs to answer with yes or no. So even with random guess, you have 50% to hit a correct answer. And the third type is that the reasoning chain is just not informative at all, though the answer is correct. And making use of the library and the evaluation metric, we did some analysis. So this 6 tasks encode maybe different skills needed for the language model reasoning, and we make use of RISE in 3 of them labeled with star. And for other data sets, since they are closed domain, we can use ground truth program to verify the reasoning chain. And first we want to see what's the effect of reward guided search. And basically we can compare train of thought and wrap to chain of thought. Yeah, basically the result is generally higher on all the tasks. One very interesting finding is that, it's not just a higher metric. We also observe there are fewer false positive chains, indicated by the smaller gap between wrap and the answer-based metric. And we found that the main reason is that reward-guided search can avoid certain types of false positive, for example, this type A. So in chain of thought, I would say the language model is already aware of the previous error, because but since it doesn't has a mechanism to regret, all it can do is to ignore the error and continue the correct generation until a correct answer is generated. But that doesn't make the reasoning chain a correct one. But for reward-guided search, it's actually able to discard those problematic reasoning steps and simply choose the correct one, so it can avoid some false positive reasoning chains. And then we also compare different search algorithms, and we found the breadth of search matters more than the depth. And I believe that because on this reasoning task, the search space is really large, so you don't want to stuck into a local maximum at the very beginning of your reasoning, so that you can only explore the more at the end of the reasoning chain, and that's what DFS does. So yeah, so on most of the cases, we really want to enlarge the breadth of the search, except on this domain where the search space is quite small, and if you maybe have a good intuition at the early steps, it's fine to explore more at the end of the reasoning chain, and that gives you some benefits. And we also want to see the effect of word model. So generally, RAP improves the performance on all the data sets, but the improvement is most significant in this blocks word task. I believe that because learning model just has difficulty tracking the object in an embedded environment, and that's actually identified in some previous research, and they claim that's because language model only learn from the web corpus instead of the interaction with the real world embedded environment. So they simply lack these skills. Yeah, so I would suggest if people want to develop LLM-based embedded agent, they may want to incorporate an explicit word model module. Okay, and yeah, we also find sometimes the format of prompt also matters. Yeah, for example, in this case, chain of thought just gives some general reasoning chain and give you a reasonable response. But here in RAP, since the format is about sub-question and sub-answers, we found this format of prompt encourage the language model to provide too many details, like the exact number. So even if the logic is reasonable overall, the exact number is not correct, and that makes the reasoning chain a false positive one. So yeah, the rest will decide it's an incorrect reasoning chain. So that's also an interesting finding that we need to put more attention on the prompt design and see whether it's suitable for the problem domain. Yeah, but it's just for this specific data set. So for mass data sets, as we can see, RAP still outperform other baselines. That's because to successfully solve a math problem, every detail matters. So yeah, you don't care about generating too many details. Okay, yeah, sometimes a certain format of prompt is easier to trigger false positives. Yeah, I guess that's pretty much of it. In this session, we talked about the reason algorithms, evaluation, and analysis on LLM reasoning. We also had a chance to go through a notebook of LLM Reasoners to see how different reasoning algorithm works in a classic problem blocks world. Yeah, I hope this session gives you a overview of the current state of LLMs and also introduction of our library LLM Reasoners. Yeah, I'm happy to take any questions.
Thank you so much, Shibo. This was my second time listening to this, but I enjoyed both time of it and learned your presentations. Are there any, we have maybe just a few short minutes left for any pressing questions.
Can I ask a question?
Of course, go ahead.
Thank you. Sure. Great talk. And I was wondering if you had any observations on which one is more common, the LLM not getting accurate premises versus the LLM getting the right facts but not drawing the correct inference. It might vary with the data set. I'm just curious if there's like an obvious trend there.
Oh, that's a good question. So yeah, I think the first one is more common because yeah, basically to understand which premise you want to choose, you really need to understand the reasoning process. But the second thing is more of a local thing. So if you already select the correct premise, then the problem can be very easy. Yeah, that's my impression.
Okay, makes sense. Thank you.
All right, so I guess we are done for today. And I'm sure Shibo will be happy to answer any follow-up questions. If you start running the code and you have any questions, I think Shibo is happy to take your questions on email. We will also share, hopefully post this recorded session on YouTube and post the link. Hopefully we will have a SIGIR VF website very soon. And thank you very much, Shibo, for the great presentation. And thank you everyone for joining us, and looking forward to having you next time in the Lean and Learn session. Have a great week.
Thank you all.
See you.
Bye-bye.